All right, so this is section 15.7b, video number 3. All right, the first two examples are relatively lengthy. Let's try and shorten this one up a little bit. So in this case, we are given one specific integral. We want to write the other 5. So let's see, we are given dz, dx, dy. So that means dx, dy is going to be our first two-dimensional projection. It might be a good idea to sketch that one. So let's see here. It says that x is going to vary from y to 1. So that means x here is going to be the equation x equals y, which is this equation right here. And it's going to go from there up to 1. So x equals 1 is right there. So x is going to vary from y to 1. So that is the correct region. I'm going to double check that just to make sure. That's the correct region. So they went type 2 on this one. So to write this as a type 1, that won't be very difficult to do. So we know z is still going to be the inner one. That's going to go from 0 to y. We'll talk about that in just a second because we're going to have to at least give a somewhat of a sketch of the three-dimensional figure here. But now we're going to go dy dx. So we're going to go type 1, which means that we're going to now go that direction. So it looks like the y part is going to go from 0 to y equals x. So that's 0 to x. And then the x is going to go from 0 to 1. All right. That one should not have been very difficult. But now let's see if we can figure out what this thing looks like three-dimensionally. So we know what it looks like as a two-dimensional projection into the xy plane. That's what this was, xy plane. So we know it's going to look something like this as a two-dimensional projection. But then it says, let's see here, in the original or in either one of these things, x is going to vary from 0 to y. I'm sorry, z is going to vary from 0 to y. So z is going to go from 0 to y, which means that the xy plane is its bottom bound, and the equation z equals y is going to be its upper bound. Well, if z equals y, first of all, this point right here is the point 1, 1, 0. But if z equals y, which is just a plane, that means if I project this thing up somewhere right around there, that means that that point right here should be the point 1, 1, 1. Since z and y are the same all the time, that's also going to be a 1. So now I kind of have the idea of this plane. It's going to start up there. It's got to go down to 0 and 0 because, again, when y is 0, so is z. So really, it's bounded by kind of that plane that you can see right here in blue. So that is going to be our three-dimensional projection. And hopefully what you can see is, and this one isn't nearly as hard, any way you look at this thing, you're going to have a triangle. If I stand over here, do some green. If I stand over here someplace or on the other side of the y-axis and you look at this thing, it's going to be triangular. If I stand over here and look at it, it's going to be triangular. And we already know that if we look and stand above it, up here, and look straight down, it's going to be triangular because that's what we've already got. So let's see if we can sketch the other two domains and then finish off writing this one. So let's see the domain, and I guess we'll just do yz first. It doesn't really matter. We'll do the yz domain. So this will be y, this will be z. So let's see here. If it's the yz plane, that means we're standing at the point which is right there and looking at it. So we know we're going to have a point at 1, 1. Put this in green. You know, we're going to have a point at 1, 1, and then it's got to come down to, well, let's see, this is a vertical line, this blue line right here, that's vertical. So it's going to come straight down, and then it's going to be angled towards the origin. So it's going to look like this. So that's your projection down into the YZ plane. It's going to look something like that. All right, so let's set up our integrals. So if it's in the YZ plane, x is first. And let's see, x is going to vary from over here, which is actually going to be from that particular plane out to, it looks like x equals 1. Because again, that's vertical. That should be going straight up. So it looks like x is going to vary from x equals y or y equals x from y out to 1. And then we just have to determine type 1 or type 2. Let's go with type 1 first. So we'll do dz, then dy. Y is going to go from 0 to 1. That's what that is. That's what that is right there. And then that's going to be the equation y equals z. So remember that this has to be in terms of y. So z is going to go from 0 to y. And then we'll do our second one, which is projected into that plane, but we'll do it as a type 2. So it's going to go from there to there, which means that it's going to be dy dz. So z this time is going to go from 0 to 1. The x doesn't change, still y to 1. And this time that's got to be in terms of a function of z, and it actually starts at that line first. So y is going to vary from here out to here. So it's going to go from z to 1. And that should be, yeah, that should be right. So then we have to do one more. Let's see, the only part we haven't done, I have to go back and actually look, we did dy dx, dz dy, so now we need to do the xz plane. So that'll be x, that'll be z. And then going back up here and looking at our three-dimensional picture, let's see, if I'm looking at this thing to the xz plane, it means I'm looking at it from over here. Well, actually from the other side technically. So again, I have a point at 1, 1. So again, I'll go ahead and put it in green at 1, 1. It is vertical coming down this way. And then it's going to look slanted like this. So it looks actually exactly the same. So again, I'm moving through it a little bit quicker, and I'm hoping you'll be able to visualize it. If you need to take a little more time initially, please do, because this is not easy. It does take time. So let's see, that's got to be dy first. We'll set both of these up. F dy, and y is going to vary from, it looks like, the slanted plane, which is going to be the equation y equals z, out to the other slanted plane. So again, it's kind of hard to see, but y is going to vary from this slanted plane in here out to that slanted plane there, which is y equals x. So we should have z to x in both cases. And then let's go, again, I tend to pick type 1 first, so we'll go type 1. So z is going to vary first, and then x. So we know x goes from 0 to 1. Z is going to go from 0 up to that function, which is the function z equals x. It must be in terms of x, because that's the last variable on the outside. And then if we change the order to a dx dz, that means we're going that direction. So again, in this case, z is on the outside, so that goes from 0 to 1. And x now goes from the function z out to 1. And there are your 6 different ways that you could write that. So it kind of is a puzzle. You're just piecing everything together and then trying to visualize, which again is probably the hardest part. All right, let's move on. So now let's actually do an example. I'm not sure if I will finish the whole thing, but at the very least, I'm going to try and set it up. So we want to find the mass and the center of mass of the solid E with the given density function rho. So they've given us the function The row function is x squared plus y squared plus z squared, which hopefully you recognize as a cube, because that's what it says. And x is going to vary from 0 to a. I'm sorry, not a cube. E is a cube. The density function is a sphere, actually. This is the e part's actually going to be cubic. It's going to be over a cube. So x goes from 0 to a, y goes from 0 to a, z goes from 0 to a. So to find the mass, we know that we integrate the density function dV over some region E. Well, I don't really need to set all this stuff up for you guys because, oops, that's not supposed to be M, that's supposed to be a row, sorry. Because it's all 0 to A. Every single one of these things is going to be 0 to A. So I'll write it on this one, but I'm not going to write it again afterwards. And then you plug in your density function, which is x squared plus y squared plus z squared. You start taking antiderivatives. You can't separate them, but everything's constant, so it makes it easier. You could do it in any order. So the dv doesn't matter. I can do it as xyz or zyx. All the bounds are the same, actually, so it makes it really simple. So finding the mass is not really that difficult. You just have to go through the process. Again, I'm not going to perform that just because of time. I want to get to the other examples. But then it also says to find the center of mass. Okay, so center of mass, we really haven't done this with a third variable yet, but it follows exactly the same as what it did before. So the center of mass, I will write this out for you, x bar is going to be 1 over the mass times the triple integral over E of, in this case, it'll be x rho dV. So all you're doing is you're introducing that extra x value that you have to multiply through. Similarly, y bar is going to be 1 over the mass, because you always have to divide by the mass, of the triple integral over E, and in this case it is just y rho dV. And then I'm pretty sure you can probably guess what z bar is going to be. Z bar is 1 over the mass, triple integral over E of z rho dV. So that's it. And honestly, given the fact that you have exactly the same bounds, you're only multiplying one variable through the density function. Whatever you get for x bar, your y bar and your z bar are going to be identical to that value. The reason for that is because the center of mass of that cube is going to be directly in the center of that cube, especially given the fact that the row happens to be spherical in nature, but that doesn't really matter as much. So you could work all that stuff out if you really want to. It'll all be in terms of some a value, but that's not what we're going to do here. So I'll just leave the setup to you. I'm sorry, I will leave the the working it out to you if you would like to. All right. The next one, we haven't really talked about this yet. So calculus can be used to do some probability stuff. As a matter of fact, there are higher level classes of probability and statistics that definitely involve calculus. I'm just going to introduce you to a little bit of it right here. So we're going to talk about this thing which is called the joint density function. And if you've taken a stats course, and you've probably already seen this before in some fashion, but a joint density function just basically means that your probabilities are going to be based upon multiple variables. In this case, they are joint between x, y, and z. So we are given the fact that the function is c, some constant, times x, y, z. If x goes from 0 to 2, y goes from 0 to 2, and z goes from 0 to 2. And f of x, y, z is going to be 0 otherwise. So it has something to do with your probabilities there. So we want to simply, in part A, find the value of the constant c. That's probably the easiest part, because in order to find the value of the constant c, we're going to set up a triple integral. So let's see. I know that I'm going to take an integral from 0 to 2, 0 to 2, 0 to 2. All bounds are constant, so the order doesn't matter. It's just going to make a difference as to which way you want to do this. But my joint density function is C, X, Y, Z. And again, I can do this in any order. I'm just going to do dz, dy, dx. It really makes no difference because all the variables are exactly basically the same type of thing. Now, here's the thing that we need to know that we hadn't talked about before. This is a joint density function. Basically, it is giving you a probability. It's saying that as long as x, y, and z are between 0 and 2, this is the function. It's 0 otherwise. So if you know anything about probabilities, is that the sum of all probabilities of a function need to add up to 1. So the answer to that has to be 1. That will now allow us to find C. C is a constant. We can pull the constant out to the front. Every one of these is constant. Everything is separable, so we can actually do this as 3 completely separate integrals and multiply them together. So let's see, the antiderivative of dz is just going to be z from 0 to 2, which is 2. So we get c times 2 times the antiderivative of dy with respect to y is just y from 0 to 2 is 2. And you guessed it, the third antiderivative, our integral, is also 2. So that's going to give me 8c on the left, which means that c equals 1/8. Okay, so there is our constant in this case. It's not really well, I guess you probably could consider this a constant of proportionality of some kind. Just remember that it's a joint density function, so it's proportional to all the variables. All right, part B. Whoops, kind of need to read part B. Part B says it wants us to find the probability of x being less than or equal to 1, y being less than or equal to 1, and z being less than or equal to 1. So it's got to be all of them. Okay, well, this is a probability density function. So really what it's asking me to find, the probability of that, I'm not going to write the whole thing, but the probability is going to be, well, c is 1/8, we know that. And we want, whoops, why didn't that write? All right, sorry about that. My pen died on me, so hopefully this will continue. Anyway, so our probability is going to be 1/8. Again, we're only talking about x going from x, y, and z from 0 to 1. That's what we're trying to find the probability of. So we want to let x go from 0 to 1, y go from 0 to 1, and z go from 0 to 1. Again, the reason we can separate those is because all the bounds are constant and the variables are separable. So that's just going to give us 1/8. Let's see. Antiderivative of x is going to be 1/2 x squared. From 0 to 1, just going to give you a half, times 1/2 y squared from 0 to 1 gives you 1/2, and 1/2 z squared from 0 to 1 will give you a half. I did not write all that out, but I'm sure you can figure that part out. So that's just going to give us 1/8 times 1/8, 1/64. So 1/64 would actually be the probability that you would get a value of x, y, and z all being less than 1. Less than or equal to 1, I should say. Now, what if we wanted to find the probability of the sum, that's part C here, of the sum of x, y, and z all being less than 1? Oops, so that's part C. That's what we're going to deal with next. And I think I'm probably going to do this one on the next page because this is going to take a bit of space. So this would be part C. So in order to do part C, let's think about what this thing looks like if we were to graph it. So let's see, we're talking about the probabilities of this stuff, of the sum of all of these x, y's, and z's being less than 1. So we know that at most z can be 1, x can be 1, and y can be 1. Okay, we know that much. So everything must lie between that plane and basically the origin. So bounded by all the planes, because you can't have probabilities less than 0. So it's going to be everything underneath of that plane. So it's really kind of the area of, or excuse me, the volume of that tetrahedron that's formed right here. It's anything within that space. So if I want to set this up to figure out how part C is going to work, we want the sum of all that stuff to be between or inside of that the volume of that space, which means that basically we're going to have to integrate in 3 dimensions. So it doesn't really make any difference which way you do it. I'm probably going to do this as a dz and then probably a type 1 dy dx. But basically you want to think of it as standing up here, looking down. I always put an X up there for like where the person is, but you're looking down on it. So my projection into the XY plane is going to go from y equals 1 to x equals 1. So if I integrate this, so the probability here is going to be 1/8, constant stays the same. Set up our integral here. It's still going to be x, y, z. And then, like I said, I think I'm going to do this one as dz, dy, dx. And again, the order is not going to matter because the bounds are all going to, well, the bounds are not going to be constant. So order actually does matter here. But we could have picked any one of the 3 places to look as a projection. So let's see, z is going to vary from 0 up to that plane. Well, the plane, so let's see, that would be x plus y plus z equals 1. Again, we want it to be all underneath of that plane. So we need to solve that for z. So z is going to be 1 minus x minus y. So z is going to go from 0 to 1 minus x minus y. And then since we're going to do this as a type 1 in that direction, let's see, I know that x is going to go from 0 to 1. That's the outside piece. And this equation right here is the same thing as y equals, the intercept is 1, slope is -1, so it's 1 minus x. So that means y is going to go from 0 to 1 minus x. Okay, and if you haven't already thought about it, we did talk about this in our other lesson. The fact that this is a tetrahedron, look at what we've got here. Okay, we've got those 2 things which are the same, and that should happen. And that's actually going to help us when we go to actually do the integral of this thing. So we're at 23 minutes right now. I am going to finish this integral off, which is going to take a bit of time, but if you're comfortable with it and you just want to see the answer, that's fine. But if you'd like to see it worked out, stick with me. Okay, so let's see. We're going to have 1/8 of, oops, I don't want to do it in orange. Let's do blue. 1/8 of integral 0 to 1, integral 0 to 1 minus x. Okay, antiderivative first with respect to z will give us 1/2 x y z squared from 0 to 1 minus x minus y dy dx. All right, I'm going to go ahead and pull the 1/2 out to the front. I'm going to start over here because this could get a little bit lengthy. 0 to 1, 0 to 1 minus x. All right, so now substituting 1 minus x minus y in, we're going to get x, y, 1 minus x minus y squared dy dx. Okay, now we do have to do a bit of work here. We're going to actually have to FOIL this out. And I say FOIL, but that's really not the correct term. We have to multiply 1 minus x minus y times itself. So let's see, xy times. Okay, there is a bit of a shortcut to doing this, but multiplying 1 times 1 is 1. 1 times negative x is negative x. 1 times negative y is negative y. So then I have to multiply the negative x times every piece, which is going to give me a negative x a positive x squared, and then a plus xy. And then I've got to multiply the negative y by every piece, which is going to give me minus y plus xy plus y squared. So as you can see, that's going to get a little lengthy. dy dx, write the other integrals down. Okay, so now we kind of have to group some things together the best that we can. So what I can see is I've got a bunch of terms in here that have just y in them. I've got a bunch of terms that have just x in them. Let's go ahead and see, can we combine like terms first? Let's try to do that. Well, yes, but let's go ahead and distribute. Let's distribute the xy first. I think that's probably going to be the easiest way to do it. So xy minus x squared y minus xy squared You know, I'm going to take a shortcut, and I apologize just because I don't want this video to run forever. I am going to combine like terms, but I'm going to do it as I distribute. So let's see. X and that X are going to combine. So when I multiply xy times each one of those, I'm going to get a negative x squared y, but I'm going to have two of them. So I'm going to do the xy times the 1. It's the only constant. So I am going to do xy. And then with the underlined red pieces, I'm going to get minus 2x squared y. Okay, and then I have to do the y pieces, and I've got two of those. So that's going to give me a minus xy squared twice, so that'll be minus 2xy squared. All right, and then we've got to deal with the x squareds. I've only got one of those, so that's just going to give me plus x squared y. Nope, I've got two of them, sorry. One here, one here. So it's going to give me two of those, 2x squared y. Okay, I'm also going to have to deal with this x squared here. That's going to give me an x cubed y. And then I'm going to get an xy cubed from the last piece. Wow. Okay. A lot of stuff. Like I said, this is going to get very long. It does fortunately start to simplify in the end, but it takes a little while to get there. All right, so let's see. I can find, let's see, what do I want to look for here? So remember that the whole concept was up in the top, we want to find things that maybe are going to give me a 1 minus x somehow. So how am I going to do that? Well, if we kind of think in terms of grouping, let's see, what can we group together here? So I've got xy's. Do I have I've got a bunch of things that have some kind of form of xy in them. Pretty sure. So maybe I'll take this term. I'll take this term. And do I have another solo y somewhere? Yes, that term. So I'm going to take those terms right there, and I'm going to regroup those together. So I'm going to have xy minus 2x squared y plus x cubed y. I did that because all those terms have a solo y in them. All right. And it looks like I made a little mistake. So you might have been asking, well, wait a minute, you have another term with only a solo y. You're right, but that's because I wrote it wrong. That should be a y squared. When I distribute the xy, I forgot to square the y as well. All right, but then I'm going to take the terms with the y squared, which is this one, and group those two things together. So that'll be plus negative 2xy squared plus 2x squared y squared. And then my last term is simply going to be xy cubed because I don't have anything else to group it with. All right, we're getting there. Just give it a minute, or 3 or 4. Hopefully not more than 5. Okay, so now let's find the commonalities. What can I pull out of each one of these parentheses? Well, it looks like I can factor an xy out of the first one, which will leave me with 1 minus 2x plus x squared. And then I can factor a negative 2xy squared, actually. So minus 2xy squared out of this one, which is going to leave us with 1 minus x. And then plus xy cubed. And this piece right here factors. That's the same thing as 1 minus x times 1 minus x, or 1 minus x squared. So I'll have xy, 1 minus x squared, minus 2xy squared, 1 minus x, plus xy cubed. dy dx, 0 to 1 minus x, 0 to 1, 1 over 16. Make sure that that's right. Yeah, I think that's probably what I want to do there. All right, so the question is, why would I want to do that? Well, now I've got y's on the outside, so now I can take antiderivatives with respect to y relatively easily. So let's see what happens. If I take the antiderivative of the first piece, I'm going to get a 1/2 xy squared times 1 minus x quantity squared minus, let's see, that's going to be y cubed, so it'll be 2/3 xy cubed 1 minus x plus 1/4 xy to the 4th dy, oops, no dy anymore, dx, and I'm going to evaluate that from 0 to 1 minus x. And why was I trying to get those 1 minus x's? It's because of that upper bound. So now if I plug this stuff in for y, I'm going to leave the constants where they are right now because I don't feel like trying to figure out the common thing to factor out. So that's going to be 1/2 x times 1 minus x, plugging it in for y, 1 minus x squared times 1 minus x squared is going to give me 1 minus x to the 4th minus 2/3 x, 1 minus x cubed times 1 minus x is going to give me 1 minus x to the 4th. Hopefully you're seeing the pattern develop. 1/4 x times, plugging in 1 minus x, is 1 minus x to the 4th. And then if I plug 0 in, that just zeroes everything out, so we're good there. All right, so now we can actually simplify this because I have common terms. Everything has some kind of a number times x times 1 minus x to the 4th. They're all like terms, so really I just need to figure out what 1/2 minus 2/3 plus a 4th is. So 1/2 minus 2/3 plus a 4th, everything's going to be in terms of twelfths. So that's going to be 6/12 minus 8/12 plus 3/12. So that's 1/12. So I get 1/12 of an x, 1 minus x to the 4th dx. Much, much shorter problem to do now. I don't want to FOIL out the 1 minus x to the 4th. I can pull out the 1/12. Let's see, 12 times 16, I believe, is 192. Don't ask me how I know that. and then I've got x 1 minus x quantity to the fourth dx. You can do this part either by using a u substitution, if you would like, or you can do an integration by parts. Actually, either way works. I think I'm just going to do a standard u substitution. I think it'll probably be easier here. So u is going to be 1 minus x. That's my composited piece. Du then is going to be negative dx, or dx is going to be negative du. Okay, so we're going to get 1 over 192. See, I'm going to switch the bounds of the integral. So that's going to give me 1 to 0. Looks a little weird. Here's the problem. If I put the u in here, u to the fourth, I'm still going to have that x on the outside. So I need to take this equation and I need to solve that in terms of x. So if I add x to both sides and then subtract u, I get that x would be 1 minus u. So I'm going to replace the x here with 1 minus u and du, and now this should be relatively simple. So I'm going to distribute the u to the fourth. So that's going to be u to the fourth minus u to the fifth du, and we can take the antiderivatives. So we're going to get 1/5 u to the fifth minus 1/6 u to the sixth from 1 to 0. And after all this, I'm really hoping this works out right. So we get 1 over 192 times, that's going to be 6 to the fifth power, I don't know that one off the top of my head, over 5 minus 6 to the sixth power over 6. And I will be completely honest with you that I do not know what those values are. Oh, that's not 6. What the heck am I thinking? That's a 0. I was going to say this is going to be way harder than I thought it was going to be. Okay, let's try that again. 0 is going to give me nothing. 1 is going to give me a fifth and a sixth, but that would have been subtracted. So really that needs to, let me erase this, be a negative of all of that. And then I'm going to have to multiply that by 1 over 192. So let's see, that's going to be 1/5 and minus 1/6. So a fifth is going to be 6/30 minus 5/30. So it's 1/30. So negative of a negative 1/30 is going to be 1 over 30 times 1 over 192, which is going to work out to be 1 over 5,760, I believe. I can double check that, but that is not much of a probability, and I know this video is like over 38 minutes, so I apologize if you did follow it, but hopefully it gave you some satisfaction to know that we got an answer. But ultimately what that's saying is the probability of x plus y plus z all being, that whole sum being less than 1. It's a very small probability, 1 over 5,760. All right, apologize for the length of the video if you kept watching, but plenty enough now to do your homework.